Okay, so 5.3 logarithms and logarithmic functions. This will be day 3. In day 3 video, you will see how to strictly graph logarithmic and natural logarithmic functions. That's it. Graphing, you're going to look at the two parent functions for log and natural log. You're going to have to know them. And we'll start then talking about your transformations, and obviously we've been doing transformations for months now, so hopefully you have your transformations down. It's just you got to know the parent functions. Okay, so let's get started. Alright, on the screen, take a look. Since logarithmic functions, here's where I'm at, I'm reading this. Logarithmic functions are inverses of exponential functions, right? We talked about logarithmic are inverses of exponential. We can derive their graphs by reflecting the graph of corresponding exponential functions over what line? Think, how do we graph the inverse of a function? What line does it reflect itself over? You should absolutely be saying it reflects itself. Okay, I know it reflects itself over that line y equals x. There is that dotted line y equals x. Okay, so what I gave you in this first picture right here, I gave you, there is the function y equals 10 to the x power. I ask you to sketch the graph of y equals the log of x. This is going to become our next parent function. So please make sure you're really paying attention and focusing on what I'm doing right now. So, some things I noticed about 10 to the x power, this guy right here. I know it has a horizontal asymptote at y equals 0. I know the key point is 0, 1. Think when I plug in 0, 10 to the 0 power is 1. So if I understand that, then on the log of x, I know some things based on understanding that 10 to the x and the log of x. Remember, the log is understood to be in base 10, so I think you get, oh, I understand now. Because that's in base 10, and this is base 10, that makes sense that they're inverses of each other. So some things that I notice that I can apply my inverses, as long as I know some things about my inverse, I think I'll be able to figure this out. Okay, first thing I notice is that the asymptote goes from y equals 0 to x equals 0, right? Remember, inverses, you simply switch the x and the y value. So I know it goes from y equals 0 to x equals 0. Something else I notice, the key point goes from 0, 1 to 1, 0. Again, switch the x and the y values. This last one, okay, think. Take this line, this exponential function right here, and reflect it over the line y equals x. I think what you'll notice is that it's going to look something like this, right? Think about reflecting that over that line y equals x. So I know the log of x should look something like that. For our purposes, this is good enough. You're going to take this sketch right here. You're going to take the asymptote and the key point. There is your parent function. I'm good enough as long as you can get an understanding of a general idea of what that looks like. Bam, we're in shape. So add this guy right here. Add that into your parent function list. Okay, so it's going to be important you understand what the log of x looks like. Alright, keep going. Now let's take a look. Next one. I give you the function y equals e to the x. There is the function y equals e to the x. I ask you to sketch the graph of the natural log of x. Remember, natural log is understood to be in base e, so it makes sense that they are inverses of each other. Okay, so some things I notice with the natural log of x. Same deal. it has a horizontal asymptote at y equals 0. It has that key point at 0, 1. So when I graph the natural log of x, I think you're going to notice, okay, so the asymptote goes from y equals 0 to x equals 0. The key point goes from 0, 1 to 1, 0. Think about taking this, e to the x, and reflecting it over the line y equals 0. Oh my goodness, it looks almost identical to the log of x. So, voila, there is the natural log of x. Add this into your bank of parent functions, right? Log, natural log, they almost look identical. So because we're doing a sketch of them, I'm okay with you understanding the general idea of what they look like. So these two questions that I'm asking you are about the log and the natural log. What one point lies on both graphs? Well, I know that that's the point 1, 0. How do the end behaviors compare? Again, talking about the log and the natural log, how do those end behaviors compare? You'll notice that they are absolutely the same. So as long as I know my two parent functions, I can apply my transformations, and I'll be fantastic. All right, so let's try some. I'm going to go slow on the first two, and then I'm going to kind of zip through the last two. All right. So, letter O. I have the natural log of x plus 2, the quantity x plus 2. How would I graph that? Well, notice it says to label both a key point and an asymptote. Think, what's the key point on natural log? What's the asymptote on the natural log? So, I know it's going to be a horizontal shift left 2. Think parenthesis. I know it shifts left to right, yada, yada, yada. I shouldn't even have to go over that stuff at this point. So, here's what I'm going to do. There is my parent function, right? I know the asymptote is at x equals 0. I know the key point is at 1, 0. I'm going to shift it left 2. So, the asymptote shifts to x equals -2. The advice that I will give you, understand that when you have log, natural log, the only time that asymptote will move is if you are shifting it horizontally. It's the only time it's going to move. Vertical shift, reflect x, not going to move, right? So understand that it's going to move when you shift it left or right, and it's also going to shift if you reflect it over the y-axis. Okay, so think about those things. So I moved the asymptote left 2. I move the point left 2, and voila, I draw my function, and I am finished. Okay, letter P. 3 transformations. Come on, you better know these by now. Draw your parent function. There it is. So think about this. If I shift my asymptote right 3, I know it's going to move to x equals 3. If I shift my point right 3, stretch it by 2 and up 1, you're probably asking yourself, well, how am I going to show that it's stretching it by 2 if I'm only drawing a sketch? I want you to think about what it's going to look like when you actually stretch something, right? Isn't it going to stretch itself out, so it's going to take longer? I'll kind of show you. Here's how quick it hooks. I think if I stretch it, it's going to just take a little bit longer, right? It's going to stretch itself out, and therefore it's going to take longer to hook. So as long as you show me that it's going to stretch itself out and it's going to hook, right, I think that I'm going to be good enough with that. So I shifted the point right 3 up 1, and I stretched it by 2, and voila, there is my new function. Okay, last two, quickly. You should probably pause the video, try to do these on your own, see how it goes. There are your transformations. Q, alright. Notice there is my parent function. I'm going to do a reflect x. So I think when I reflect x, watch what happens. Here is my original parent function. Right, there it is. If I reflect x, I think this thing is going to look something like that. Right, think those points, these points here have to go up here. Those points here have to go down there. So I think I understand what a reflect x is going to look like. Okay, so reflect x, shift it up 3, voila, there it is. Letter R. Notice I just kind of skipped the parent function. You should be trying these on your own. So I just kind of went right to the answer. Shift it right 1, reflect it x, voila, there it is. Be careful. You know I'm going to ask you, label the asymptote. Understand where the key point is. I'm going to ask you that, so please make sure you label, show me where the point is, and good job.